So good morning, everyone. And again, it's a pleasure to see most of you live and some of you, I guess, on Zoom. So I'm going to discuss a framework called fractional diffusion-advection-asymmetry equation. And this is the equation that I'm going to discuss. In it, you'll see this fractional space derivative. And the main topic is actually explaining letters with only one only recently. In the second part of the talk, I'm going to discuss work with Raffaella Burioni and Alessandro Besani on the rare events in this system. So as a starter, let us imagine all of us going to some pub in Cambridge, and we go as a group, or if you want, you can think also, but we're going on some hiking expedition. And what will happen to this group of people? I think you know it from your daily experience. So first of all, there is a bias, and the bias in my talk will always be to the right. So Cambridge is here, and we start here. That what's reasonable to think about this is that the population density, the concentration of particles, which are people in this example, will be first of all non-symmetrical. Some of us will be drinking or doing something, and they'll be trapped behind. And I'm going to claim that this is very common also in physical processes, where due to trapping, some particles stay far behind the main peak of the motion, and this will be this red line is the shape of the density of particles, and again, everything is moving to the right. Now, when you look at this picture, you immediately understand a few things. First of all, this is not a Gaussian process, lifting and diffusing, expanding, but there is certain asymmetry here. And the claim of my talk is that when you deal with these type of diffusions in complex environments, you need to think about 3 transport coefficients. Usually we think about 2 of them, but I say we need to think about 3 transport coefficients. The usual ones are diffusion, that's the drift, and then the asymmetry of this thing. All three objects are important phonologically. So, okay, this is some very basic motivation. Direction, of course. Yeah, sorry. So we will present this fractional advection-diffusion-asymmetry equation, and this will be presented for transport in disordered system using the continuous time random walk. There are 3 transport coefficients and not only 2. And a special case is the physical meaning of these space fractional derivatives in kinetic equations. And it's related to work, experimental work that Mark Marshall has contributed a lot to this. So what is this equation? I'm just writing the main result. We have a density of particles, or could be also probability density, and you have the usual time derivative, then you have the usual diffusion, you have the usual drift, and then the fractional asymmetry comes here in the last term with this type of Wright-Riemann-Liouville equation. And I'll discuss this later. So we have transport coefficients, D, V, and S. S is from symmetry breaking the symmetry. The question is, what are these what are these transport coefficients? And these are related to, first of all, some drift. So in a random walk process, we have the size, microscopical size, average size of the jump. That will be denoted by A, and you have the variance of the jumps. Though both of them are going to be finite, so we have no evyflights. Even though we have here a fractional space derivative, there's no evyflights here, but still we get this thing. So we will also assume, like in continuous time random walk, that we have these probability density function of these waiting times, and they fall like a power law. But here, importantly, beta is between 1 and 2. This means that the average time between jumps is finite, but the variance is infinite. So many talks in this conference were dealing with beta less than 1. I'm talking about beta bigger than 2. And we have these Einstein-like relations that these are very common. These are relation between the diffusion constant that comes here. This is sigma squared, size of the jump, the variance divided by the average time between jumps, the velocity is the average size of the jump divided by the time between jumps. It's completely standard. And then you have a symmetry breaking, that's the new part, which is also related to this bias A. It goes like A to the power beta and some amplitude that depends on time. So the big surprise, or maybe interesting in my mind, is that from these power law waiting times, my claim is you can get fractional space derivative. And that is confining, and that is a bit surprising in my mind. And that also can cause some a debate that is in the literature already that I'm going to discuss, how this can be. Okay. So I'll try and explain the debate also. So first of all, the fact that transport is not symmetric is known for a long time when you have a bias. It's important that only when you have a bias you see this non-symmetry, when you have some driving force in one direction. If you have no driving force, this does not happen, this symmetry breaking. So this is some simulations in a porous medium. This is millimeter scale. And as time goes by, this is in 2 dimensions. So the bias is in this direction. And in the long time limit, you see this type of shape of the density of particles. There is a symmetry breaking in the direction of the bias. And this was discussed in the context of hydrological flows, traces in contamination, etc. And clearly, first of all, the diffusion is not Gaussian in these things. And here I'll show you one example of this, but there are many. So here we have some sand and some, here we have some blocking events, blocking states. And there is a drift, and you see here these red traces. They're going in this direction, and you see that they have this long tail. And this is very simple because some of the particles are trapped behind, and they are moving slower than the other particles. Importantly, in all my talk, I don't have any paths. In these experiments, there are no paths. We cannot see the paths. We can see only the density of particles. And this is very important because this causes some spreading. There was a lot of work done by Mercharet, and very famous work and very important work that modeled this type of transport in a very different way. No waiting times, but Levy jumps. But Levy jumps which are not symmetrical. So if you look at the figures of Mercharet, he modeled this type of processes using asymmetric Levy flight that would create non-symmetrical shapes. Non-symmetrical packets, and these are related to space derivatives in an obvious way, which is well known. So my claim is that you can get the space derivative either from time or from space jumps, either from the jumps in space or from the waiting time. And then it's very hard to distinguish between these two processes. Because it can model many systems. So this is, for example, a mathematician writing in the you have a particle, it jumps here. This is on a 2-dimensional lattice. You have these power law waiting times, and you have the jump length displacement, which are going to denote by f of x. And we have 2 long tail distributions, again with a finite moment. Different than the flights. Equation he proposed. The equation he proposed, you see here, contains these non-symmetrical possibility of non-symmetrical shapes. So if P is equal 0, then you have these non-symmetrical Levy jumps, exactly like what we have. But what is the difference? The mechanism. He claims that we have Levy jumps. I claim we have long waiting times. And it looks like a contradiction. But he already, this group, or Mark's work, already proved that this is a worthy thing to mimic data. But the interpretation is the issue. For me, at least. Okay, so we will let us see how this happens. So let us describe the main result. We have a distribution of jump lengths, and it's given by there is a finite variance. This is a finite variance, which is sigma, and a finite size of the jump, which is a. This is related to the force that is driving you to the right. You have these power law waiting times with some beta. Now, the important thing is that you have the probability of making n jumps in some time t, and then the probability to find the particle at x at time t is the probability to make n jumps at time t, and then you have the probability to find the particle at x given n. This is well known, and this is subordination, but now we have a subordination slightly different than what we had in many talks. So if you look at textbooks or mathematical works, for example, Katolsky from 1995, but I think it's even known better before that, this QTN, this probability in the regime where beta is between 1 and 2, it goes to a Levy distribution, which is non-symmetrical, of course. It's non-symmetrical because you cannot have negative n, actually, so it's non-symmetrical. So this is a well-known result. I'm replacing this n, this sum with an integral in the long time limit. This is allowed. And here is the limit distribution of QTN in the long time limit. And what is the limit distribution of this fx given? Well, it's a Gaussian because I assumed finite size of jumps. Now I have this integral, and here you see the Levy and the beta comes in here. The definition of this Levy, it's a non-symmetrical level density whose Fourier transform is given by exponential minus I k beta. And from here you see where the fractional space derivative will come out. Now, all you need to do is you need to think a little bit that you are allowed to extend this zero actually to minus infinity. The and then you change variables and you define a limit. And then when you go back to Fourier, let's take the Fourier space, then you get this equation. And this is in Fourier space. And here you see the fractional derivative in space. The boundary conditions are free. And you see here, second, that's the usual definition. You see the definitions of different transport coefficients. In particular, you see the drift is proportional to A as usual, but also the asymmetry is proportional to A to B. So if A is 0, this guy and this guy will go away and you'll have only diffusion. So for very weak forces, you go back to the usual diffusion. They are not independent, these two transport coefficients here and here. Diffusion constant, the velocity, and here is this symmetry breaking, and here is this equation. And what happened previously that people had this type of equation without this, and in some cases they said, oh, if we have this by model, it's a Levy jump, it's Levy flight, but it's not, or it could be, or we don't know. This could come from the weighting. So this is just simulation now in 2 dimensions. So here is the theory, and here is the simulation. Simulation is continuous time random walk simulation, very simple simulation. And we also add the y direction, where in the y direction there is no bias. So in y direction you actually have simple diffusion, and that's why you have these type of I call them eyes, this symmetry breaking. And here I have this a weak bias, so this is more or less Gaussian, and I make the bias a bit stronger, and then the symmetry is breaking is bigger, it's more stretched. This will try, similar to the simulations that were performed previously by Brian. So, okay, so the question is, with this type of equation, is this a practical tool? So I'll not go too much into the details, but in some of these experiments, what they do is they change the bias as a function of time. Now, you can solve these type of problems with, let's say, a continuous time random walk if you wanted to when you change the bias, but that would be horribly complicated. My claim is that with this type of time changes of the bias, which is controlled by the experimentalist, who can easily solve the equations I presented before, and this is the merit of this approach. You can solve at least the problems where there's fluctuations in force, and I'm not going to go into these details. Let me just show you what happens to the density of particles. So here we show an example where the A bias is kind of weak and the time is not so long. And we simulate the process, and we also present the simulation of the equation. And what you see here, because the bias is relatively weak, you see here as the Gaussian, because the asymmetry is controlled by the bias. This is the long time, very long time limit where you will converge eventually to this non-symmetrical state. But for finite times and very weak fields, you get simply a Gaussian. So usually in our discussions, we throw the Gaussian away to the rubbish, but it's not true because it depends on how strong is your bias. That's the main point here. On the other hand, when I make the bias stronger, I converge to this Levy density. The Levy process is winning. I mean, the fractional is more important than the diffusion part of the equation. So strong bias, Levy wins, weak bias, Gauss takes over. And you cannot say that one of them is more important than the other. So, okay, we got some referees, some were good, some were bad, and then one of the referees, maybe one of these two guys, said, let us try and explain how come do I get from waiting times how do I get fractional space that look like evyflights? How is this possible? And apparently there was some nice one sentence, but very nice sentence in this paper from a long time ago, explaining how the waiting times are related to long jumps. And the idea of this Sydney week is the following. This is a physical idea. We have waiting times, tau 1, tau 2, and as I mentioned, they are parallel distributed. Now let's go in our mind to a reference frame that is moving with the velocity of the packet. So now I have you are moving. What will happen to these rest times? If you are moving and the particle is staying, you see the particle as if it's jumping like a evyflight. Because when you go to the reference frame of moving, those guys who are resting are moving like a Levy walker. And that's why when Sweeney and Wick said that trapping times in one reference frame look like long jumps in space. This is also what we get. We get this fractional space derivative, but it has nothing to do with long jumps in space. Depends on your reference frame. Okay, this was just some motivation to think about. Then we had, of course, also a very bad referee. So they say, oh, the case against Levy kind of partial derivatives is well known, and that is that the fractional kinetics with fractional space derivatives that claim to be non-physical in the following sense. The mean square displacement diverges, but obviously for the random walk, the mean square displacement has to be finite. Nothing diverges there because you have these waiting times. So what is happening here? What is happening here that you have the rare fluctuations in this left tail, you need to treat them very carefully. The equation breaks down in the far left tail, and this is the second walk. I hope I have a little bit more time. I think I started a bit late. So let me discuss this. Following. We have this density of particles. It's a function of x for some time, and it looks non-symmetric. Now let us look at particles here close to this peak, and let us look at particles down here in the tail. This is what I call rare events down. So guys, it's very simple. If you look at their specific trajectory, so I'm at time t, I look at their trajectory in the computer, what happened is they made some jumps, but then they got stuck for a very long time, all during the whole measurement time. On the other hand, if I look at the particles that eventually are found here at some time t, they made a lot of jumps, all of them small. They didn't get trapped so much. I think it's obvious. Now, we say the following, okay, you have this long sticking time. This is the maximum of the all sticking times. If I will know the statistics of maximum trapping time, then I'll know something on the far left tail. That's the idea. Okay, it might be easier said than done. So what we do is the following. We have these waiting times, a 1, a 2, etc., and then we have until some measurement time t. The last time is called the backward recurrence time, and we are looking at tau max, which is the maximum of all these times. Then this is a problem in extreme value theory, but these are correlated because the sum of all these guys is finite time, but it is related to extreme value theory. Recall again that we have this parallel waiting time and want to calculate this thing, the distribution of this thing. But before we do that, what we do, we in the simulations, we have the position of the particle from one trajectory, and along this trajectory, we can look at the largest sticking time along the trajectory. And then our claim is that when you have these rare events, the small x behavior that you practically did not move, then x, position of the particle, is t minus the maximum trapping time. So this is the remaining time move. Divided by the average time, remember beta is bigger than 1, multiplied by the average size of the jump. And you can think that this is reasonable, and or you can also do simulations, and we can also prove this actually. And you do simulations, and you see here, I plot the x and the 1 minus tau max minus t, and you see here the rare events, they follow this straight line. There is a very strong correlation for small x close to 0, the guys who didn't move, x and tau max, or the following way, which is expected. Now, what do we actually do? We need to calculate these rare events on this side, and we need to calculate this tau max on that side, and we show that in distribution, this guy and this guy are the same. In that sense, we can improve this more mathematically. So let me concentrate on this tau max. The result, so I'm defining tau max, longest trapping time, divided by t. So this psi is between 0 and 1, because the biggest tau max cannot be bigger than the measurement time. So this is between 0 and 1. And here I show the probability density function times this psi times the scaling function. This is the probability density. First of all, there is this what I call typical fluctuation, which is this line, and it stretches over. This is a well-known result. It's called the Fractional distribution. The Fractional distribution describes the largest out of 10 random variables if they have a power law distribution. But the Fractional doesn't work because it neglects the correlation and it goes on to infinity with the power law. So it's not exactly capturing this. So what we are interested in is not only just the total distribution, but the tau max close to t. And here I'm showing you the theory. This is the line. And there is a cutoff here at 1. Why is there a cutoff? Again, because tau max cannot be t. And well, you see that the simulation and the theory work well. And what is this theory? This theory says the following, that the probability density function of tau max is given by this function I of this scale variable, because the fluctuations are of order of t. And this is this expression for this function I. It's given by this sum of these two terms. I'm not going into the details. You can go and read my papers if you are interested. And with Rafaela and with Alessandro, we got this result. And this, you can think about this result as some correction to the rare events of the Fractional distribution. Now we can do the same for the x position, and this is the PDF of x, and I write it in maybe a slightly strange way. This is psi, this is 1 minus xa t over tau. This is exactly the translation of x into the longest waiting time, and you see that it has the same feature at large x. So this proves that this small x, this is small x is close to 1, is the same as the largest maximum time, and these two things related. And why does this solve the MSD problem? It's very obvious, because a cutoff. There's no particles going backwards, so there is a cutoff at 0. You have this Levy tail, and then there is a cutoff described by this function that I just now described, describing the rare event, and that gives you the MSD is finite again. It means the fractional equation describes the center part of the propagator, but not the rare events. I'm just summarizing. We have these non-symmetrical shapes. In this far tail, we have these very long sticking times, slow events. We can calculate the sticking time and relate this largest sticking time to this cube. The solution of the fractional equation continue here to minus infinity. So here the solutions are non-physical, but these are really rare events that if you measure particles, you never find particles here anyway. So, okay, the fractional equation continues to the left too much, but we don't really care. If you want to go into these details, you need to look at these corrections around here. But otherwise, the solution of the fractional diffusion equation with this symmetry breaking is well describing this system. Finally, I want to say that we worked all the time with beta less than between 1 and 2. What will happen if beta is between 0 and 1 and you add a drift here? This is a well-known equation called the fractional Fokker-Planck fraction. And here the beauty is that this is the fractional time. So what is happening here, when beta is less than 1, we have a fractional time. This is some old work with Ralph Metzler and Yosef time ago. The fractional time, you get fractional time when beta is less than 1. You get fractional space when beta is bigger than 1. And there is a beta equal 1 is a very tricky thing. And I don't know exactly what happens there. But there is a transition in the equation itself from the description of time to space. Of course, when beta is equal less than 1, left tails, we get right tails. Right tails because can say that this order is very, very strong when beta is less than 1, and all the particles are stuck at the beginning. So we are walking to some pub in Cambridge, but there's something that is attracting us, and we cannot leave the room here. So exact opposite. This is a right tail, left tail, because tapping is more pronounced here. Okay, so I want to thank you for listening, and I'm sure all of you want to have some coffee. So. Again, I was motivated by this work on contamination in geological formations by the group of Mark. There was a debate between this. Some people, Weitzman was saying this is related to time on the walk with trapping times. They were saying this is related to long jumps in space. I just showed that the two approaches are related somehow, and this is all related to fits a fractional space derivative, don't necessarily interpret it as comes in space. It could be time. This is my message. Experiments, okay, focus on concentration of particles, trajectories in this field, combination field. So it's very hard to distinguish between non-symmetric level jumps and continuous time around the world. So what would Mark say if here? Might be some physical motivation for Levy flights. It's not that I'm saying that Levy flights are impossible. The idea of Mark was that there is some turbulent mechanism driving this contamination. This turbulent mechanism gives you these Levy flights. And what he did is wrong. I'm just saying that there are two interpretations on this data, and there is a dispute between these groups. What is the thing and how can you solve the dispute? If you can follow single trajectories, you can see the paths, and then you can say this group is right and this group is wrong, but they look only on concentration. Very hard to do.
And now it is time for questions and remarks. Do you have?
So yes, I just was curious about the dispute with the second referee of physical review letters with this objection about the variance. So how it ended in the end, because I mean, people can make calculations and see that there is nothing wrong. So I don't know.
Well, I mean, the mean square displacement in physics, but not only in physics, but statistics, has this appeal because of the Gaussian. And then people believe that the mean square displacement is the most basic quantifier of transport, and maybe they are correct. We cannot argue with this because this is the reality. So in physics, some people would say, okay, you have this fractional space derivative, but we know the MSD is finite. So no, we cannot accept this equation because it cannot even give the mean square displacement. But how was it solved? It was very simple. I had 3 other referees who say this is very interesting. It was actually chosen as edited suggestion, and they understood that the rare events, that the MSD is in some sense a very bad quantifier because it depends on the far tail. So the MSD is a moment that is sensitive, very difficult to measure. So I would say even you should not measure the MSD at the beginning unless you have extremely good data. Measure the low order moments, x to the power q, and q is less than the index of the beta of the fractional derivative.
More questions?
So thank you very much. I would like to ask you 2 comments. One on the dimension of these processes, like is there any differences in going from dimension 1 to 2 to 3, etc. And second, like you start from this random walk with jumps, the continuous counterpart process, can you explain me a bit more what is it and how to rescale the random walk to get something that reflects the same type of behavior but moving in a continuous fashion, so no, without jumps?
Okay, so the second question is more complicated than the first. So let me start with the first question. So I just go to the beginning. The claim is that if you want to go to higher dimensions, so assuming that the bias is in one direction, let's call this the x direction. This bias is affecting the function of the derivative only in the x direction. If you do not have bias in the other direction, and of course, if you have bias in one direction and the other direction, let's say it's a constant, you'll have some direction. And then, so what will happen when you have this process and you have a higher dimension? In the directions which are not in the bias, it will be simple diffusion. This is what these I shapes. Because in the other directions, the A is 0, so S 0 there. Okay, so I don't see there's no big problem in this framework and this is actually what we did in our figure. Now, with respect to the paths, so okay, this is a bit more complicated because I'm saying that the origin of my process is this waiting time distribution, so I believe that. Okay, first of all, I'm not a mathematician, but I believe there's something more deep. So, but you see, this equation is like a subordination. So you have this Gaussian process, and n is like operational time, and then instead of using this usual subordinator, you have this non-symmetric Levy distribution. So you can define this. There is there's some subtlety here. When you look at the limiting distribution of this Q again, the mathematical literature, they continue it to n to the minus infinity, as if the time can be negative. But this is not important because of the bias. So there is some subtlety. But then you can define a process with this subordination. Possible. But on the other hand, I want to emphasize you could do this without any subordination, but with jumps. Just want the density. So it depends what you look at.
Well, it's maybe a very naive comments, but Levy process when beta between 1 and 2 is not subordinator, yes?
I don't know what you mean by Levy's process.
Levy process is,
here in space,
no,
it's a Gaussian.
This is L beta.
Yeah.
If beta between 1 and 2 is not subordinator. So you kind of change time using scaling of this, but I mean, it's a little bit tricky because of it's not subordinator. Subordinator only when beta between 0 and 1. That's a mathematical fact.
Okay, but
So
why not to have
how you can subordinate? How you can subordinate, let's say, some Gaussian into time which is not subordinated, which is not going just up. So, but my comment maybe that's maybe idea that you have to consider the running maximum of this process, and this running maximum is well studied. There is a and this running maximum of this Levy process became similar to subordinator. And even distribution of it related to another subordinator when beta between 0 and 1, not beta, but transform beta. And there is even fractional equation for this running maximum. There are such a papers in probability. So in my view, this is some sort of idea. I'm not sure that it works. Instead of subordination like subordinator Levy process of stable Levy process of order beta between 1 and 2, to use a running maximum of this process.
Okay, I mean, possibly, but okay, so for me, there's different meaning of subordination, okay,
yes,
as a simple physicist. One of them is just to transform the process from this time to the real time t. So you can take the density and you do this, what I call subordination to the whole density. Okay. You are talking about a transformation on the paths, the paths themselves. So in principle, you can do that with these waiting times. This is the original process that have these power laws with beta between 1 and 2. Yeah, and then you can choose Levy functions which are non-symmetrical in that regime, and you can do that, and that will converge to this. But we didn't look at the path so much, because again in this field we look at the densities. But again, for me this is subordination, because instead of taking this Gaussian, you can take different types of solutions and then map them from the Gaussian process to the other process. But that is a transformation at a given time t, not all the path.
Okay, thank you.
Are there questions from Zoom? Yes, I think so.
Yeah. More comment to the last question too, Eli. You're absolutely right that
Hi, Boris.
what you have is a subordination, and actually the subordination in the original sense of Bochner, where you subordinate against another process. Where the beta less than 1 is coming from is now to go to a semi-Markovian process where you subordinate against an inverse process. But the original where you actually subordinate against the density of a process goes way back to the 40s of subordination of Bochner and then Feller and so on. So this is very much a subordination.
Okay.
Thanks.
Thank you.
Okay, thank you very much. We have something in chat. Is it?
No.